So the next talk is going to be by Danai Patsiou, and it's establishing standard toxicity testing for engineered nanomaterials in the aqueous phase.
Thank you. So I am Danai Patsiou, and I am a PhD student at Heriot University.
There. What happened?
Okay. Oh, yeah. Thank you. So nanoparticles are particles with all three dimensions in the nanoscale, between 1 and 100 nanometers. Nanoparticles can occur naturally in the environment. We can find them in the ocean spray or in volcanic ash. Or they can be man-made, engineered nanoparticles. Nanotechnology is widely used nowadays, and especially in the food industry or cosmetics, sports gear, so they can be released accidentally or during or after application. So the nanoparticles, because of their nanoscale properties, they have unique physicochemical properties. So they have surface charge, and they can form weakly bonded particles, so they're called agglomerates, or they can be strongly bonded together, and they're called aggregates. So the toxicity of the nanoparticles has been increasingly studied for the last 12 years. However, it is difficult to assess the ecotoxicity of the nanoparticles. It is really challenging to measure it because nanoparticles often undergo significant changes during the exposure period. So, for example, because of the agglomerates, they can settle in the exposure vessel during the exposure period, or the dissolution. So, for example, the metal nanoparticles can dissolve metal ions, and also changes on the surface of the nanoparticles can occur. So, to address the settling of the nanoparticles, our research group recently published a study where exposure chamber was designed. So we can see here, this is a glass beaker, and there is a chamber in the middle. So the nanoparticles, the zebrafish larvae are held inside the chamber. There is a mesh in the bottom that separates the larvae from the rest of the beaker. There is a pump, there is a tube, an air tube, where air pumps and bubbles, and there is a magnetic stirrer, so the nanoparticles are held in suspension throughout the exposure period in a zebrafish toxicity test. So this design improved the toxicity testing of the nanoparticles. So as we can see in the graph A, the concentration of silver nanoparticles is kept consistent throughout a 96-hour exposure period, in contrast to a static beaker, where actually after a few hours there are no nanoparticles measured in the water volume. So more consistent concentration of the nanoparticles was found throughout the exposure duration, and that improved the reproducibility of the results. The limitation of this study was that actually the beaker and the exposure chamber was set in a 2-liter beaker, so this makes difficult, routine acute toxicity tests, and also creates lots of waste. And that leads to the aim of our study, that is to further develop a standardized procedure for nanoparticle toxicity testing in the aqueous phase, to improve the test reproducibility. And we also compare the nanoparticle toxicity testing across different methods. So we have our exposure chamber, we have the static glass beaker, that's a traditional exposure method, and we have a 96-well polystyrene plate. Also, in parallel, we have conducted freshwater algae Chlorella vulgaris toxicity tests. That is important as a control because offers a limited sedimentation of the nanoparticles throughout the exposure period because of the constant agitation of the solutions. So specifically, we have the polystyrene 96 well polystyrene plate, where one larva was placed per well, and in a total volume of 200 microliters. And then secondly, we have the static glass beaker, 100 ml, we had 15 to 20 larvae per beaker in a 40 ml total volume. And our third exposure method was the exposure chamber, where it was held in 600 ml Pyrex glass beaker. We had 15 to 20 larvae per beaker and in a total volume of 450 ml. Our Chlorella vulgaris toxicity tests were conducted according to the OECD guideline number 201, and the total volume was around 50 ml in flasks, Pyrex glass flasks, and the growth inhibition was estimated out of the chlorophyll A measurements. So the nanoparticles that we use for this study are commercially important nanoparticles with wide use. We used silver nanoprisms, PVP coated. We used cerium oxide nanoparticles stabilized with HMT, titanium dioxide nanospheres stabilized with tetramethyl ammonium hydroxide, and copper oxide nanoparticles. We also used silver ions out of silver nitrate as a control toxicant. So silver ions are completely dissolved in water, and that is in direct contrast with the nanoparticles that are not soluble. So the first set of the results, now we have the silver ions. The immortality of the zebrafish larvae was modeled using the logistic regression with independent variables, the nanoparticle concentration, in this case is the silver ions concentration, the treatment, that is the three different methodologies that we used, and the concentration and treatment interaction. So the orange curve is the mortality produced inside the chamber, the green curve is the static beaker, and the blue curve is the 96 well plate. We see that the zebrafish concentration response curve did not differ between the chamber and the static beaker. However, significantly reduced toxicity was found in the 96 well plates. So now it's silver nanoparticles, and we see that the toxicity inside the chamber was found very high, with an LC50 of 220 micrograms per liter, where in contrast the static exposures, both static beaker and 96 well plate, were significantly lower, with an LC50 of 15.5 and 13.5 milligrams per liter, respectively. So at the right, you can see the growth inhibition of Chlorella vulgaris with the concentration of silver nanoparticles. The cerium oxide nanoparticles, we see the same pattern. The toxicity produced inside the chamber is higher compared to the static methods. So we have in the chamber an LC50 of 57 milligrams per liter. We didn't find an LC50 in the static beakers, and there was no mortality inside the 96 well plates. The copper oxide nanoparticles have again the same pattern, higher toxicity inside the chamber with an LC50 of 20.4 milligrams per liter and an estimated LC50 of 212 milligrams per liter inside the plates, but no mortality up to 200 milligrams per liter in the copper oxide nanoparticles inside the glass beakers. Sorry. So the titanium dioxide nanoparticles, we found no mortality up to 200 milligrams per liter concentration in both static exposures. Inside the chamber, there was some mortality. However, there is no significant response with the concentration, and we didn't model that response. So to sum up, the nanoparticles toxicity inside the chamber was found higher than the nanoparticle tested in any static condition. But there was no additional mortality of the zebrafish larvae inside the exposure chamber. So can we relate the toxicity that we see to the surface to volume ratio? Because as you can imagine, there is differences in the surface to volume ratio across the methodologies. So the theory is that the higher the surface to volume, then the toxicant sorbs to the surface and the less toxicant is available for the fish. So less toxicity is found when we have higher surface to volume ratio. And we can see that the chamber is significantly different from well of the 96 well plates. So if we actually relate the data that we have in the toxicity with the LC50 values to the surface to volume ratio, we can find a nice correlation for the silver ions, where actually, but however, there is a completely different pattern for the silver nanoparticles, so they don't behave like the silver ions. So the take-home message is there are differences in toxicity between in the same material between different methodologies tested. There is lack of maintenance of aqueous phase nanoparticle dispersions, and that is a major limitation in testing nanoparticle ecotoxicity, and that highlights the need to establish standardized nanoparticle toxicity test protocols. The exposure chamber that is presented in this study can maintain nanoparticle suspension for a 96-hour exposure period. And I would like to thank Alice Tagliati and Rosa Alexander, the Zebrafish Research Group from Heriot University, and the Nanosafety Research Group, and thank you for listening.
Thank you. Time for 2 questions.
So the take-home message for me is like, this research will change the industry, or how are you seeing this? Apart from, yeah, we need robust protocols to test toxicity, but what would you tell the industry then?
So nanoparticles, nanotechnology is relatively new technology, and that's why we struggle to assess the toxicity, because nothing is established yet. We don't fully understand the toxicity that the nanoparticles can have. So the chamber offers an opportunity to see possibly the worst scenario. It's not that this scenario is the real scenario. In some cases it might be, in some cases it might not, but for the risk assessment, this chamber can offer data that will be useful.
I have a question.
Yes.
Do you think the same differences in results that you've seen between these different methods, do you think that would also hold true if you have different types of nanoparticles? So, for example, ones that have a positive versus a negative surface charge, or...
Yes, of course, nanoparticles behave differently. And as we saw in the few nanoparticles that were selected for this study, we saw different patterns. So chamber was toxic, but then there were differences between the static exposures. So sometimes we didn't see toxicity in the glass beaker, sometimes we didn't see any toxicity. So it depends on the material, it depends on the coating, it depends on the surface charge. There are so many variables actually that we need to have in mind in order to assess the toxicity.
Great. Any other questions? No? Okay, thank you very much.
Thank you.